So we've talked a lot about gas laws. Laws say what happens. We've got all these equations. We can calculate one thing if we have this other information. Now we're going to talk about a theory that explains why gases behave the way they do. And this is called the kinetic molecular theory. So kinetic refers to motion. Molecular refers to molecules. And so this is a theory about gases based on the movement, the motion of their particles. It's the simplest model. So in this model, we think about a gas as a collection of particles. Those could be molecules or atoms that are in constant motion. So they're constantly moving. And unlike solids and liquids, well, liquids move dimensionally, but solids just move in place, right? They don't move relative to each other. Gas molecules are traveling through space. So there are several ideas in the kinetic molecular theory. The first one is that the size of a particle is negligibly small. Based on the overall volume of a gas, the size of the particle doesn't matter at all. In fact, we go so far as to assume that the gas particle occupies no volume. Does that mean it has no volume? No. It just means that the volume is so small it doesn't matter. So, don't remember if I've used this analogy before, but I live in Reedley, there's this fruit being packed and shipped all over the place. You see big semi-trucks full of oranges will be coming up in a couple months. So you see this big semi-truck with this open trailer of oranges, and they need to weigh this on the public scales. So they go over there and they weigh the truck, and as they're pulling away, somebody says, "Hey, you dropped one." They got one orange. The guy's like, "Okay, we'll just toss it up there." So you toss it up onto the truck. Does he need to go reweigh the truck because he's got one more orange on there? No. Does the mass of the orange matter? Not compared to the mass of the truck full of oranges, right? So that's talking about the mass of a single thing in a big, big group. We're not talking about mass for the size for the gas particles, but we are talking about the size. Maybe a better analogy is I've mentioned Wyoming and how I think of Wyoming as being a lot like a gas because there's so few people in Wyoming. So there's 400,000 people roughly in the whole state. If you add one more person, is that going to affect crowding in the state of Wyoming? No. Because in the overall scheme, that one person has no volume. They take up no space. So there's so much space, empty space, between the gas particles. And the empty space thing is kind of hard to think about because you think about, well, what's in the room? I mean, there's benches and people and stuff, but what's this stuff up here is air, right? So in the air, there are little tiny gas particles. What's between the air particles? Nothing. It's empty. It's kind of hard to think about. At STP, argon atoms occupy only 0.01% of the gas volume. So if an argon atom was the size of a golf ball, the closest next argon atom would be 4 feet away. So think about a golf ball, not very big. The next one's 4 feet away. So the actual size of that particle doesn't matter at all. Any questions about that? The average kinetic energy of the gas particles is directly proportional to the temperature in kelvins. When you increase the temperature of the gas, the average speed of the particles increases. Temperature is a measure of average kinetic energy. When you heat a gas, the kinetic energy increases, the particles move faster. So they're traveling through space faster. It's important to understand that this is the average speed. Not all the particles are moving at the same speed. There's a distribution. Some of them are slower, some of them are faster. but the average goes up when you increase the temperature. Any questions about that?
Would the distance between the particles decrease, or would they stay the same?
That's a good question. Would the distance between the particles decrease or stay the same? It would stay the same, because if you're not changing the volume, they're still occupying the same overall volume. It's just that they're moving around in there faster. Now, is that going to affect the number of collisions? Yeah. They're going to collide harder and more frequently. So that's going to affect the pressure if you don't allow the volume to change. Good question. Any other questions? Third statement, the collision of one particle with another or with the walls of its container is completely elastic. What that means is that when the two particles collide, they can exchange energy, but there's no overall loss of energy. In the macroscopic world, the world that we can see, we don't observe truly elastic collisions very often because there is a loss of energy each time things collide. Probably the closest thing we've seen in real life is perhaps either an air hockey table or a pool table. So on a billiard table, you've got the hard round balls, and you hit the cue ball, and it rolls, and it runs into another ball, and it hits it. The overall energy, if it's a completely elastic collision, does not decrease. The energy can be transferred from one to the other, but the overall energy stays the same. So here's an example. The pool balls, right? So here they're coming in this way, two balls meeting, they collide with each other, they bounce off, and they keep going. Roughly the same speed leaving as they had when they hit. An inelastic collision would happen between two balls made out of clay or something soft. You roll those towards each other, and they're just going to go thunk and stop. They're not going to bounce off of each other because it's inelastic. The kinetic energy that they had, the energy of movement, gets dissipated as heat when they bump into each other. So gas particles just bounce off of things, and it doesn't affect the overall kinetic energy. This dates me, but I remember when the first computer game came out, Pong. I really need to get a YouTube video of this because people are not knowing what this is anymore. But the way Pong worked is there was this little blip, and it would move in a straight line until it hit either the wall of this box or your little paddle at the bottom. And you could just move this paddle right and left. This was really, really cool, right? So you move this paddle right and left, and you try to keep this little blip from falling through the bottom. And sometimes you could get it set up so it would just keep going by itself forever. You get it in a loop just right. The little blip never slowed down because in a computer game, you don't have to have friction if you don't want friction. That's what gas particles are like. So gas particles are like a big, complicated game of Pong. Any questions? So that's the kinetic molecular theory of gases. Gas pressure follows conceptually from kinetic molecular theory. So KMT is really long to type out, so sometimes it's abbreviated KMT, kinetic molecular theory. So the gas particles are constantly moving, that's what the theory says. They strike the sides of the container with force. The result of many of those teeny tiny particles exerting forces on the surfaces around them is pressure. So pressure is force divided by area. Gas particles are hitting the walls of the container with force. There's an area of this, the surface of the container, and that's the pressure. Kinetic molecular theory explains Boyles Law. Boyles Law says that the volume of a gas is inversely proportional to the pressure. So if the volume goes up, the pressure goes down, and vice versa. If we decrease the volume, that forces the gas molecules into a smaller space. in that smaller space, more molecules are going to be colliding with the container at any given time. And so the pressure goes up. You're taking those moving particles and you're squeezing them into a smaller volume. They're going to hit the sides more frequently, causing the pressure to go up. Charles' law says the volume of a gas is directly proportional to the temperature, the absolute temperature. So kinetic molecular theory says if we increase the temperature of the gas, the average speed, and thus the average kinetic energy of the particles increases. Now, when we looked at Charles' law, the pressure needed to be constant. So if we're increasing the kinetic energy of the particles, they're going to be moving around. They'll collide with the sides more frequently and with greater force. And so that would increase the pressure. But we're trying to keep the pressure the same. In order to keep the pressure the same, we have to expand the container. So if you increase the temperature, the volume of a gas at constant pressure will increase. Avogadro's law explained. Volume of a gas is directly proportional to the number of gas molecules. If you put more gas molecules into this container, they're going to hit the sides more frequently, and that would cause the pressure to go up. But in this law, we keep the pressure constant. And so in order to keep the pressure constant, the gas must be allowed to expand. Volume increases when you add more particles. Any questions? The laws were observed first. Scientists observed, this is what happens when I do this, and discovered patterns and stated the laws. Kinetic molecular theory came around later to explain why those things happen. Daltons Law, we can explain this as well. Daltons Law says the total pressure of a gas mixture is the sum of the partial pressures of each of the gases in the mixture. So, kinetic molecular theory says particles have negligible size and they don't interact with each other. When they hit, they don't say, "Hi, how are you? Let's go hang out and form a molecule." They just bounce off of each other. So, particles of different masses are going to have the same average kinetic energy at a given temperature. You familiar with the equation for kinetic energy? Kinetic energy equals 1/2 mass times velocity squared. Two particles with different masses can have the same kinetic energy. What that means is if the mass is larger, the velocity is less. If the mass is smaller, the velocity is greater. So small gas molecules will be moving faster on average than large gas molecules, but they all have the same kinetic energy. Because the average kinetic energy is the same, then the total pressure of the collisions is the same. So it doesn't matter what the gas is. So when we look at this mixture of gases, each gas is going to exert a pressure that's dependent on the volume and the temperature and the number of particles, not on their size. And so that's why the total pressure is the sum of the pressure from each gas. So behavior predicted by KMT is consistent with the observations and the measurements that are made of gases. Scientific theory is the most powerful kind of scientific knowledge because this gives us insight into why things happen, how things happen, and that allows us to investigate and predict future things. Now, the ideal gas law, that word ideal is in there for a reason. The ideal gas law does break down under certain conditions. But when we look at those conditions, that actually helps us understand even more about gases. Okay, so we kind of mentioned this. the average kinetic energy of gas molecules depends on their mass and their average velocity. So, in very simple terms, the kinetic energy is 1/2 the mass of the particle times its velocity squared. It's fall, got football on my mind, so go to football games every weekend. And so I think about the football players. And so you've got these smaller, more agile guys like the running backs, right, and the receivers. They tend to be smaller physically than the big linebackers. We got a guy on our line that's 360 pounds. I mean, he's just huge, right? Who can run faster? The 170-pound running back or the 360-pound linebacker? No contest. The running back can run faster. Can they both have the same kinetic energy? Yeah, they can. So if you think about these two guys running into you, right? Big guy doesn't need to be going very fast to just knock you flat. But that lighter guy, he's going to have to be running faster to exert the same amount of force when he hits you, right? So this is how gas particles are. The big ones are kind of moving slow. The small ones are quick and fast. But they pack the same punch if they're at the same temperature. Does that make sense? So if the gas particles have different masses, then the only way for them to have the same kinetic energy if they have different velocities. So instead of V for velocity, we use this URMS. So that is the root mean square velocity. So it's kind of a special sort of an average. So think of it as average, but it's not your regular average. There's reasons behind it, but we don't want to go into that. It's close to the average velocity. So we can say the kinetic energy is 1/2. This is the number of molecules and the mass of them and the root mean square velocity squared. That sounds funny, doesn't it? The root mean square velocity squared. So in a gas mixture at a particular temperature, the lighter faster are particles. The lighter particles travel faster than the heavier ones. So we can derive this equation. Pretty sure most of you are not interested in the derivation of all these things. So if you are interested, it's outlined in the textbook, and if you want to talk about it, I'd be happy to talk about it, but I'm not going to torture everyone with that. So this equation is important. The root mean square velocity, the average velocity of this gas particle, is equal to the square root of 3 times r times the temperature divided by the funky capital M. What's all this in here? Well, 3 is just 3, so that's nice. R is the ideal gas constant. But here, because of the units on the other things, we're going to use the ideal gas constant with different units. So we're going to use this value that's 8.314 joules per mole Kelvin. We're using joules here instead of liter atmospheres. I don't expect you to remember this value of the ideal gas constant, so I would give that to you. Here, this script capital M is the molar mass, and we need to have this in kilograms per mole. So the molar mass here has to be in kilograms per mole, and that's so that the units work out. So calculate the root mean square velocity of gaseous xenon atoms at 25 degrees Celsius. Is it Friday yet? So root mean square velocity, that's that URMS. Well, we were just introduced to an equation for that. 3RT over funky M. So R is just a variation of the ideal gas constant where we've changed the unit. It's joules per mole Kelvin instead of liter atmospheres per mole Kelvin. T is the temperature. Well, they're giving us the temperature in here. We're dealing with gases. We have to use the absolute temperature. So it needs to be Kelvin. So we'll convert this to Kelvin, 298 Kelvin. And then script M is the molar mass in kilograms per mole. They didn't give us a molar mass. But they told us what element it is. It's xenon, so we look at the periodic table. That says 131.3 grams per mole. Grams per mole. So we can write out the conversion, or we use the prefix milli a lot, don't we? Milli and kilo both involve moving the decimal point 3 places. The issue is what direction. So what we want here is we want kilograms per mole. So I'm going to look at the size of the unit. This unit is small. A kilogram is large. So large unit, I need a smaller number. For the small unit, I need the larger number. So converting grams to kilograms, I need to make this number smaller. So it's 0.1313. What I'm doing there, without writing it out, is I'm using this conversion factor. Now I have R. I've got temperature in Kelvin. I've got my molar mass in kilograms per mole. I can plug all these things into the equation. So square root of 3 times 8.314 joules over mole kelvins times 298 Kelvin divided by the molar mass in kilograms per mole. That looks like kind of a mess, doesn't it? Let's see what happens with the units here. So we've got Kelvin, that's what that is. Kelvins cancel and the moles cancel. So let's do the math on the calculator. So 3 times 8.314 times 298 divided by 0.1313. So this is going to be the square root. I'm just writing this down as an intermediate to show you what's happening with the units. So the units I have left there are joules per kilogram, right? And I have to take the square root of that whole mess. So when I take the square root, I get 237.925. If we're thinking about significant figures here, the 298 has 3, so this would have 3 significant figures. Now, joules per kilogram, the square root of joules per kilogram does not seem like a rate of speed, does it, of velocity? A joule is equal to a kilogram meters squared per second squared. That's the joule in terms of the SI base units. So if I have joules divided by kilograms, like I do in here, that means I have the kilogram meter squared per second squared divided by kilograms. So that gives me meters squared per second squared. When I take the square root of that, I get meters per second. So the unit on this rate of speed here is meters per second. So 238 meters per second. You do not need to know how to do this. If you're good with units, that may be easier than just memorizing. Otherwise, use the correct units over here, and then just remember that the rate of speed here is meters per second. Any questions? So we talked about the temperature is the average kinetic energy. So there's a distribution of velocities. There's a distribution of kinetic energies. So if we look at the number of molecules in a given gas with a specific velocity, we see sort of a bell curve. So for oxygen, the velocity, the molecular velocity, there's basically none that aren't moving, and as you increase the velocity, we see more and more particles until here, this is the largest. Most of the particles have this velocity, and then as you go faster and faster, they taper off. And an interesting thing is that as you look at smaller molecules, so oxygen has a molar mass of 32, the molecule. Nitrogen is 28, water is 18, helium's 4, hydrogen's 2. As you go to smaller and smaller masses, the distribution spreads out. So for a small gas like hydrogen, which is the smallest thing there can be, it has a very wide distribution. There's a big variation in how fast the particles are moving. As the gas particles get larger and larger, the distribution narrows, and it becomes narrower. We also see effects on the shape of that distribution with temperature. So as you increase the temperature, here we're looking at the same gas, but we're increasing the temperature. This is 273, this is 1,000, and this is 2,000 Kelvin. So we see that this peak, where the largest number of particles is, the velocity of those increases with temperature. But we also see that these curves spread out as you increase the temperature. When we spread these out, the effect is that we have more particles with faster speeds. So, any questions? A lot of concepts in there.